Another Yucca Mountain one. I don't know if that's good or bad. I won't read it, but I'll bring it in. Well, I won't read it. But this is basically the question is this. We talked before about Yucca Mountain, which is a repository. I guess I can't draw on this, so I can't. So you remember that we said that Yucca Mountain is a repository that is, in this particular case, 350 meters deep. Water table is at 600 meters. What would happen is if you put a whole bunch of hot canisters of radioactive waste, is it will basically boil off the water that is present within the formation. And in the same way as if you evaporate water from a lake, it goes up into clouds where it condenses at some height where it becomes cool enough to condense. What would happen underneath Yucca Mountain is you can imagine that at the level of the repository, if you look at the temperature of the repository, it'll be high, maybe 160 degrees centigrade. But as you get further and further away from the repository, above or below, it will cool down just by conduction, right? This is just a thermal gradient. So in other words, heat is being conducted both upwards and out of the system and also down into the earth. But once you set up this once you set up this temperature gradient, if you look at the places where it is above boiling, say 98 or 100, there are reasons why it's 98 in this particular case, but it could be 100. Then above here, any vapor that's migrating upwards might condense because now it's less than 100 degrees centigrade, and so you'll basically get a static cloud in the formation that the water will want to fit itself into. And the question basically is asking, if you boil out all the fluid that is present in the repository between 350 meters to 250 meters, and if you calculate that volume per column, which is a meter by a meter in plan area, is there enough space for this to fit above it between 250 meters and the surface? So that's what you're being asked. You have some information that says something about how porosity varies as you go up in the section. Relative low porosity is quite high up. So these are, this is the surface at 0 meters. This is the water table at 600 meters. So it's depth below surface. So you know, whoops, didn't mean to do that. You have the porosity in the units. You have the existing saturation in these units. And the question is, within the pore space, is there enough space to have all of the water that you generate from 350 meters to 250 meters plus the amount below it from 350 meters presumably to 450 meters. That stuff will also go buoyantly, right? It'll rise up. So is there enough room for that all to fit in this region here? And so to do that, you basically have to think about this capillary pressure versus saturation diagram to be able to think in terms of how would you think about it? So you have a capillary pressure versus saturation diagram. It looks something like this in terms of saturation of water between 0 and 100%. You know in the material that's at the top, so this is the repository. So this is 350 meters. This is 250 meters. This is 450 meters. If you take everything that's present within this zone here and you try and stuff it in here, question is there enough space? So you know in this region here what the saturation of water is. So presumably if you're boiling it off, you can calculate how much water you can remove from this because you know you're on this curve somewhere at some saturation. And so presumably if you boil it all off, you can calculate how much water is present there as a saturation. And if you know the porosity of this and also its height, which I'll call uppercase H, then these terms together should give you something about the volume of fluid you can produce. If you know the volume of fluid you can produce, you should be able to work out whether it fits here, because you know that in the material above it, you're also at some different saturation, and I suppose you can calculate whether you would be able to get in enough fluid into this relative to these ordinates on here. So this is the irreducible water saturation. So you shouldn't be able to get any more water out of here, but then you're boiling it off. So you have to think as to, if you boil it off, do you actually get out of this region and go all the way to this axis? You need to think about that. If you're boiling it off and putting it in here, and you're trying to cram it in from some initial saturation, do you go this amount, or do you go this amount? Again, that's for you to rationalize as to what you think and give the reasons for what you think. And so you'll come up with some answer as to whether it'll fit or not. So that's one part, as to whether it fits within the porous medium within it. The other part is that when this happens, what it will do is it will be pushed into these fractures, which will then get it sucked into this other material. Because remember, I've only drawn one curve here, but the other curve, I guess, that we should draw is this. So this is drainage out. This is imbibition in, and it's really related to this. So as soon as water touches this really fine material, it gets sucked into it from the fractures. But the other thing you're being asked is that if you had a fracture above here, so if you have a repository that sits here, that has some vertical fractures, which it does, and if you, in this zone above 250 meters, relative to 350 meters, all the way up to the surface, can you fill these fractures up with water? And if you did fill them up with water, would you be able to hold them by holding it up as bootstraps by its capillarity? And so the questions are two. One is, how much volume can you put in the fractures in addition to the pore space, which is the first question. And that's just another volume question like this. And then I guess the other question, I think, I haven't looked at it very carefully, is to know whether the size of these fractures, which you can relate to the permeability, and the spacing between fractures. So in other words, these fractures would be spaced by some amount, and you can look at the question to figure that out. So in other words, if you know the permeability, can you calculate what the apertures of these fractures were? And if you do calculate what the apertures of these fractures are, you can probably calculate how high a column of water you could hold in these. We have an expression which is something like, well, I don't want to give all the stuff away, but it's something like yes, it's so increase, if you increase this, you reduce this. Oh yes, so interfacial tension. So it's not equal to, I think that's right, but otherwise it's proportional to. So in other words, clearly if you have a fracture which is big, you can imagine it'll take a large volume of water, but you can't keep any height in there. If you reduce the size of it, then all of a sudden you'll start being able to take a measurable height. And as you get smaller and smaller, the height will increase, maybe until you get all the way to the surface at 250 meters. Actually, you could do from this, if you know what interfacial tension of water is, which is, I think, something like 2 millinewtons per meter. This is milli, not meters. Then you could calculate what aperture you could have to get 250 meters of water. And you could also use that to calculate what the permeability would be. But that's basically the question. Again, if you're using more than 2 pages to be able to figure it out front and back, you're doing something more than you probably need to. You do it. It should be quite compact. So it's nothing more than a volume problem. It's not really a complicated calculation about saturations with capillary pressure curves given in this. It's really a volume. If you remove the volume of water here, does it fit into this portion here? Okay. All right, thank you.